All right, everyone, and we're back for the last half of section 4.3, subspaces. Remember, subspace of a vector space is a subset that is closed under addition and scalar multiplication. Now, we left off with this theorem, or at least we begin with this theorem, that says if A is an m by n matrix, the set of all vectors in Rn such that Ax equals 0 is a subspace. Okay, that subspace is called the null space of A. Now, this is a hugely important result, okay, and it's something that we can prove, okay, that the null space is an actual subspace, and it's in fact something that we already have proved. If you remember back to, I brought out the textbook number 16 in section 2.3, consider the m by n homogeneous system of linear equations, the set of all x's such that ax equals 0. Okay, and we looked at parts A and B. Okay, well, what was z? Z was the sum of two vectors such that ax equals 0 and ay equals 0. Okay, and we showed that az equaled 0. So that meant it was closed under addition. Okay, and c was a scalar times x, aw happened to be 0. And so that means it's the subset would be closed under scalar multiplication. Okay, so I'm not going to go through that again because we did it in class. But what I am going to do is I'm going to pick up on, well, before I get to the examples, I'm going to kind of show you a picture of what the null space of A is representing. Okay, so let's take a look. Okay, A is an m by n matrix, as said in the statement of the theorem. Okay, and we're multiplying the matrix A by a vector in Rn. Okay, so you want to think of this as the domain. Okay, and now when you have an m by n matrix times an n by 1 vector, what are you going to get out? You're going to get out an m by 1 vector. So we are mapping into Rm, not Rn. Okay, now we can't presume that when we multiply a vector in Rn times A, we are going to get all of Rm. We're going to get some of Rm, or most of Rm, or even all of Rm, but we're not guaranteed to get all of Rm. Okay, so this purple circle is describing the collection of vectors in Rm that gets mapped to by multiplying by the matrix A. Now, there's a very important element in Rn, the domain, that's 0. Anytime you multiply n by the zero A by the 0 vector, okay, anytime you multiply any matrix A by the 0 vector, you're going to get 0 as your output. So 0 always gets mapped to 0, and so that's why it's going to be in the purple circle. Okay, but it's not true that 0, it's not always true that 0 is the only thing that gets mapped to 0. Okay, there could be a whole collection of vectors that when multiplied by the matrix A gets mapped to 0. And this collection is what's called the null space of the matrix A. It's a fact that A times the 0 vector outputs 0, but it could be the fact that A times the vector 1, 2, 3 gets mapped to 0, in which case the vector 1, 2, 3 would be in the null space of A. So you want to think of it as the piece of the domain that gets mapped to 0 in the range. Okay. All right, so hopefully that helps. If not, please feel free to ask about it in class on Friday. But we're going to move forward with the first example. Okay, I gave you a matrix A, the vector 2, 1, 3, -6, -3, 4. And I'm going to find the null space of A. Okay, so let's do that. I'm looking for the set of all vectors. So here's the matrix A, 2, 1, 3, -6, -3, 4. I'm looking for all the set of all vectors. Let's call them x, y, z that gets sent to. So that's a 2 by 3, that's a 3 by 1, so the 0 vector. Okay? So what do these vectors have in common? Or what characterizes this set of vectors such that when I multiply it by the matrix A, I get out the 0 vector? Okay, so let's take a look. So this matrix equation corresponds to 2x plus y plus 3z equals 0 and minus 6x minus 3y plus 4z equals 0. Okay, we're solving a system of equations. Now we can do it with an augmented matrix. I'm going to encourage you to do that. So let's look at what an augmented matrix looks like. 2, 1, 3, -6, -3, 4. Augment that with 0 and start doing elementary row operations. So as we do it, let's see. And we can kind of go through this a little bit faster because row reduction is not the purpose of the problem, it's part of the problem that we're solving. So let's see. If I wanted to put this in row echelon form, I could take row 1, multiply it by 3, add it to row 2, and that could be my new row 2. So 2, 1, 3, 0, dot, dot, dot. 6 plus -6 is 0. 3 plus -3 is 0. 9 plus 4 is 13, and 0 plus 0 is 0. Okay, so that's the first action I would do. And then I would scale the bottom row, 0, 0, 1, 0. Again, these are steps that in the past I had you write out. Okay, now we're just kind of doing them as we go. Now we're going to multiply row 2 by 3 and then take the difference between row 2 and row 1. So that's going to be 2, 1, 3 minus 3 is 0. That's 0. Row 1 stays the same. And now this is in row echelon form. Okay? We don't even have to get it to reduced row echelon form. This will suffice because this corresponds to, and I'll write this in red, the system of equations 2x plus y plus 0z equals 0, and 0x plus 0y plus 1z equals 0. So what can I conclude from this? Okay, well, there's a couple things I can conclude. Okay, I can say that, well, this is 0, this is 0, this is 0. I don't need that. I can say that 2x is equal to -y. I can say that z is equal to 0, and y can be anything it pleases. Okay, this restricts z to be 0. This restricts 2x to be -y, but there's no restrictions on y. So y can be anything we please. So I can let y equal y. In fact, the book will say, don't let it equal y, let it equal r, which makes this equal to -r. So that means that x is equal to -r over 2. Y is equal to r, and z is equal to 0. So the collection of vectors, remember that was the whole purpose of doing this, the collection of vectors that when multiplied by the matrix A outputs 0, 0, are vectors that look like this. Okay, so vectors that look like this. Okay, so this is not something that I would ever expect you to show, but I'm going to kind of list some vectors out, okay? They look like, what? -1/2, 1, 0. They look like negative, well, if r is 2, what's that? -1, 2, 0. They look like, what happens if r is 4? What, -2, 4, 0, and so on. So they're all the vectors, the null space of A is the set of all vectors that are of the form r times, and here's the neat thing, I don't like fractions, so I can say it's -1, 2, 0. R times the vector -1, 2, 0, where r is real. And you can confirm that, okay? Let's take a look at taking a vector. Let's make r 8, okay? So we're confirming this result via an example, which is not really a confirmation, but it's just checking, I guess. We'll check for the reasonableness of our solution. Take the matrix 2, 1, 3, -6, -3, 4, and let r be 8, okay? So if r is 8, then that's -8, that's 16, and that's 0. What does that equal? I don't know, let's see. 2 times -8, that's -16. Plus 1 times 16, that's 16, plus 3 times 0, that's 0. -6 times -8, that's 48. -3 times 16, that's -48. 4 times 0, that's 0. What vector is this? It's the 0 vector, okay? So, just because it worked for one doesn't mean it works for them all, but it confirms that this description of what I have for the null space of A seems to make sense. All right, one problem done. Use the backside of this. Okay, what about the null space of A, where A is the matrix 1, 4, -1, -2, -7, and 3, 1, 2, and 4. Okay. Well, again, we're going to run to the augmented matrix. So augment this. Because we're looking for the set of all vectors such that AX is equal to 0. So the right-hand vector is the 0 vector. So we can just make this 1, -4, 1, -2, -7, 3, 1, 2, 4. Again, I'm trying to streamline the process a little bit because nobody wants to be doing this for days. And let's do some row reduction. Let's add rows 1 and 3 together. You get 0. You add that, you get 1. You add that, you get 5. Okay, and let's multiply row 1 by 4. That would be our new row 2. So 4 minus 4 is 0. -8 minus a -7. So -8 plus 7, that's -1. 4 minus 2. 4 minus 2 is 2. And that's 0, 1, 5. Okay. And let's add rows 2 and rows 3 together. So 1, -2, 1. 0, -1, 2. 0, add this together, 0, add that together, 7. Okay. So let's do 2 steps in 1 here. 1, -2, 1. That's 0, 1, -2. Okay, and make that 0, 0, 1. Okay, I'm just scaling both rows 2 and 3. All right, so now let's multiply row 3 by 2 and add it to row 2. So 0 plus 0 is 0, 1 plus 0 is 1. Negative 2 plus 2 is 0. 1, negative 2, 1. So everything here is nice. Okay, I have a pivot, pivot, pivot. The only thing I need to correct to put this in row reduced echelon form actually are these two elements right here. So let's subtract row 1 and row 3 together. 1 minus 1, 0 is 1. Negative 2 minus 0 is negative 2. 1 minus 1 is 0. 0, 1, 0, 0, 0, 1. And let's add row 1 to 2 times row 2. So it's 1, and negative 2 plus 2 is 0. 0 plus 0 is 0. 0, 1, 0. Oh no. 0, 0, 1. I totally whiffed on this. I forgot to augment this. 0, 0, 0. 0, 0, 0. 0, 0, 0. Nice thing is, because it's a zero vector, every time I scale and combine, I'm getting zeros. That would not be true. There we go. Sorry about that. That would not be true if this weren't the 0, 0 vector. Okay, so I told you I was going to augment this and I didn't do it. All right, there we go. What does this tell you? Okay, this tells you that's x1. If you wanted to do x1, x2, x3, x1 is 0. Okay, this tells you that x2 is 0. That tells you that x3 is 0. So for this matrix, the null space of this matrix consists of one vector, the 0 vector. All right. So sorry about the mistake on that, but hopefully you caught it and we're yelling at the video to correct it. Okay. Next, look at the set S of vectors x, y, z such that 3x plus 2y minus 8z is 0 and x minus 5y plus 6z is 0. Is that a subspace? Okay, so there's a couple different ways to approach this problem. Okay, there's a direct way. Okay, and so let's try the direct way. We let the vector, I don't know what you want to call it, let's give it u. Let u be the vector x, y, z, and let v be the vector ABC, such that 3x plus 2y minus 8z is equal to 0, and that a minus 5b plus 6c is 0. Okay, again, they're just two vectors in our set, and because they're in our set, they have the property that 3 times the first component plus 2 times the second component minus 8 times the third component is equal to 0. And looks like that x minus 5y plus 6z is equal to 0. So x minus 5y plus 6z is equal to 0, and that 3a plus 2b plus minus 8c is equal to 0. Okay, and then we'd say let u plus v equal, and we would add the vectors u and v together, and you get it to be x plus a, y plus b, z plus c, and you want to show want to show that the vector u plus v has the property that 3 times the first component, x plus a, plus 2 times the second component, which is what, y plus b, minus 8 times the third component, z plus c, is equal to 0. And that the first component, so that'd be x plus a, minus 5 plus the second component, y plus b, plus 6 times the third component, z plus c, is equal to 0. And that's very doable, okay? Because what you would do is you would distribute the 3, 2, and negative 8 through the first equation, the negative 5 and the 6 through the second equation. You'd organize all your x's together, x, y, z's together, and all your abc's on the others together, and you'd say, by assumption, 3x plus 2y minus 8z is 0, and x minus 5y plus 6z is 0, so half of this equation be equal to 0, half of this equation be equal to 0, and this would say the other halves are equal to 0, and 0 plus 0 is 0, okay? That's a lot of work, and there's a better way of doing it, okay? So, when you look at this, okay, you're looking at the set of vectors such that two equations are equal to 0, okay? So let me flip the page upside down. Okay, that should remind you of the process that we just did, okay? So you have 3x plus 2y minus 8z is equal to 0, and x minus 5y plus 6z is equal to 0, a system of two equations. Okay, systems of equations can be converted to matrix equations. So what would the matrix equation look like? Well, it would be xyz times something is equal to 0, 0. What would that something look like? It would look like 3, 2, negative 8, 1, negative 5, 6. So this is the matrix A, this is the generic vector x, and this is the 0 vector, okay? And they're asking us, okay, to look over, when I take the set of vectors such that this condition holds and this condition holds, so this is the set of vectors such that when multiplied by a you get out 0, is that set of vectors S a subspace? And the answer is yes. Why? Because the set S is describing the null space of the matrix (3, 2, negative 8) and 1, negative 5, 6, and we just stated that the null space of a matrix is always a subspace. Well, that was a lot easier. So all we had to do was notice that this set S was describing the null space of the matrix 3, 2, negative 8, 1, negative 5, 6. And when you do that, because we could convert this system of equations to a matrix equation that was of the form AX equals 0, and by all this stuff, especially this very, very powerful theorem that I started lecture off with, we could say that it was a subspace. Again, this only works because the right-hand side is equal to, I should point to here, zeros. All right. So, where is the last page of notes? There we go. This it? All right. For examples, I'm not sure that we'll do them all just for the sake of the length of the video. We're already 25 minutes in. Let S be the set of all vectors such that 5x1 plus 3x2 is 1, 2x2 plus 6x3 is 1, and x3 minus 3x4 is 1. Okay. So, what are they describing here? Okay. So they're describing the set of all vectors x1, x2, x3, x4 the output is 1, so that's 5, 3, 0, 0. That's 0, 2, 6, 0, and 0, 0, 1, negative 3. They're describing the set of all vectors that when multiplied by this matrix outputs 1. And the question that we have to answer is that describing a subspace? Well, just got done telling you that this being 0 is relevant, okay? So the fact that it's not 0 makes me think that this is not a subspace. And if it's not a subspace, all I have to do is find one example of it not being closed under addition or scalar multiplication. Okay. So, how to do that? Okay, we know if this were a subspace, then it would be closed under scalar multiplication. So that means that if x were in S, then C times x would also be in X, as would 0. Now, why? Well, because we're assuming that this is a subspace and it's closed under scalar multiplication, then the C times X would also be in S for any C, including the scalar 0. And 0 times this vector would be a 0. So 0 would have to be in our subset S. That's one of the facts that we talked about in the previous video. So I guess the only thing that we have to do is to show that it's not a subspace, is to show that the 0 vector is not in S. So let's show that 0 is not in S. How do we do that? Okay, we'll take our matrix 5, 3, 0, 0, 0, 2, 6, 0, and 0, 0, 1, negative 3, and multiply it by 0, 0, 0, 0. What do you get? You get 0, 0, 0, which is not 1, 1, 1. So the vector 0 is not in S because A times the 0 vector is not equal to 1, 1, 1, 1. There you go. Oh, sorry, I was out of the screen for the last of it. All right, so that's kind of how you look at the first problem. Example 2. Is the set of all possible multiples of 103 a subspace? So you're looking at S as being the set of all possible multiple. So r times 103, where r is real. It's a scalar. Okay, so I don't have any intuition on this. Okay, so I'm just going to say, let's pick two vectors. Let u and v be in S. So that means u is equal to some vector r, or some scalar r, times 103. And v is equal to some other scalar, let's call it s, little s, times 103. So, question, is u plus v in S? So that means, is u plus v some scalar times the vector 103? Oh, let's see. What is u plus v? It's r times 103 plus s times 103, which gives us r plus s, 0, 3r plus 3s. Well, this is equal to r plus s times 1, 0, 3. Factor out an r plus s out of all of that. And you get u plus v being a scalar times the vector 103. So it's closed under addition. Now what about scalar multiplication? So is c times v in S? Now remember, v was the vector s times 103. So if I take a scalar and multiply it by s,